to be entertained and hopefully informed at the same time. I imagine that most of you are in this audience because you're interested in climate change. If you're here for the salsa dance class, you missed it. Climate change. Things are getting warmer. Why? We'll talk about this. But before we do, I always like to start off with something humorous. And this one seems to be rather appropriate to this particular subject because we don't know which way to go. This is me. I have covered the first one, the second one, and the third one. The fourth bullet I'll talk about very briefly. During my career after 9/11, I was involved in emergency response, dealing with terrorism that may involve radioactive materials. And in fact, our research changed New York's emergency response plan. The other bullets I'll talk about later. I don't want to waste any time. Right, what is climate? All of the energy that is coming in to our environment comes from this object here, which is our star, our sun. All of the radiation coming from that interacts with our planet. In the different spheres here, the atmosphere, the biosphere, the cryosphere, the geosphere, the spheres, and that energy reacts with them in different ways, impacts them on different ways, and of course, from climate, we get weather. Do not confuse weather and climate. Climate is the overall umbrella that controls weather. Weather is what happened today, had nothing to do with climate, although climate did influence it. Just because it's cold today doesn't mean to say the climate's getting colder. If it's hot today, it doesn't mean to say the climate is getting hotter. But this weather can be very highly variable the more energy we put in to the climate, and that I'm sure you're all familiar with now. Weather is becoming more extreme around the world because we're putting more energy into the climate. So this is the question I'm sure that is on some of your minds, and some of you will be in the yes camp, and some of you will be in the no camp, and some of you will be firmly in the middle going, I really don't know what's going on. Maybe this guy on the stage is going to tell me. What I would like to do is present to you facts and let you go away and make up your own minds from the information I present to you today. So first of all, I want to show you the result of a rather large survey that was done a couple of years ago now, 13 countries, 26,000 people around the world, and the numbers that you can't see there too clearly, unfortunately, are all in the 80s, so the average there is 82% of people in those countries think we should be using more renewable energy as our energy sources. From the same survey, they've ranked the 5 top concerns. Number 1 is terrorism. Might seem a bit odd to you, might not. Number 2, however, is climate change. That is the number 2 concern to most of the people. In fact, 66% of that survey are concerned with climate change. These are their attitudes. So where you see the purple color, we want to use more of it. And where we see the sort of gray color, we want to use less of it. These 3 here emit greenhouse gases, and you can see some people want to use substantially less of coal, some people want to use substantially more of biomass, and natural gas seems to be evenly split. And then there's the others over here, renewable energies that depend on weather conditions at the time. Let's have a look into the past about planet Earth and see what's been going on, so you can gauge what today's weather looks like and today's climate. So this is the oxygen content of planet Earth going back a long way. We're actually going back 1 million years, and it was only about 650 million years ago that we started increasing oxygen concentration on the planet as life started to evolve. Takeaway message from this is don't take oxygen content in the atmosphere for granted. It can change, and as you can see, it's risen higher than where we are today. This is where we are today. It's been lower, and in fact it is slightly declining now in the oceans, and it has been since 1960, so things can change. And of course, if we lose oxygen, we're all in serious trouble, aren't we? Ice. We've got ice on the planet. We seem to have 3 thermostat settings on planet Earth. One of them is the greenhouse. There's no ice sheets whatsoever. One of them is the ice house. That is some permanent ice. And the other one is the snowball, where we've got a frozen planet. I'll talk more about that one in a minute. This is a shocking statistic. through our 4.5 billion year history, only 15% of that time have we had ice on the planet. What does that mean? Meaning we are living in an unusual time, because 85% of the time on the planet there's no ice. So whether we're accelerating climate change or not, it's going to go away at some point through a natural cycle. And I'll talk more about the effect of that fairly soon when I get to the sea. Now, we do have natural cycles. These are known as the Milankovitch cycles. They were discovered in the early 1900s by a scientist called Milankovitch. This is the precession of the Earth. You know, the Earth is spinning on the axis, but the axis is not vertical, it's slanted. And that slant actually changes as well, just by a small degree. But both of those affect the amount of heat coming down to the land and to the sea. Cycle here, about 26,000 years. This cycle, about 40,000 years. Then this is the orbit of the Earth. This is exaggerated, so it is not a circular orbit. And as that orbit changes eccentricity, it also affects the amount of energy coming into the Earth. And that cycle, as you can see, is about 100,000 years. Similar cycle, too, as the orbit is precessing around the sun. But that one doesn't affect the climate so much. Yes, they're natural cycles. And as they coincide, we will get an effect like this. And this is the sun energy coming in at 65 degrees north, and as the warmer part of one cycle there adds to the warmer part of another cycle above and so on, we will get warmer periods here, we will get colder periods here, and these gray bars correspond to regular periods. Now, the periodicity of ice ages has changed. The amount of ice present has changed with time, and we don't quite know why. This is a complex slide, but I want you to understand one thing from this. So what are we looking at? This is the temperature proxy on planet Earth. This is the carbon dioxide proxy. You notice they are not lockstep with each other. There are other things in the past that have driven climate. It is not just CO2. There are other effects that do this. Right now, we seem to be in a position where they are in lockstep, and I'll talk about that as we go on. Looking back over the last 540 million years, these are two studies here. They're both telling the same story. This is sea level compared to where we are now, which is here. So as we go back about 100 million years, sea level was about 100 meters higher, or 200 meters higher if we go far enough back. What's a meter? If you're American, think yards. Who lives in Florida? You were underwater in those days, completely. The state was gone. And it's gone down, it's gone up, and it just depends on how much ice we've got. So sea level can change drastically depending on the climate. If we are to melt the ice caps that we have today, and as I said, whether we're doing it or it's going to be a natural cycle, they will go at some point. Sea level is going to rise about 80 meters or 260 feet. It's not going to affect us in our lifetime, but it is going to happen at some point. Look back 60 million years. This is the temperature proxy, so you can see how it's gone up and down. This is the Eocene hothouse period. I'll talk more about that in a minute. And after that cooled, the Antarctic ice sheet started to build in somewhere around 35 million years ago. The northern hemisphere ice sheet started building in somewhere from 25 to maybe 10 million years ago, and they won't last forever. So that's looking back over 60 million years. This is the Eocene hothouse. So we're looking back 55 million years ago, and you can see that things look very different. There's India still heading towards Asia to collide and form the Himalayas. Florida's underneath that box, completely underwater. There's little islands there that is the United Kingdom. So that's what it was like when there was no ice on planet Earth. These boxes here, which are in centigrade or Celsius, are above the average temperature, which is there in the Gulf of Mexico, which was about 27 or 80 Fahrenheit. Looking back over the last million years, now we're looking at temperature and CO2. So the blue is the CO2 concentrations, and we're going up to just over 300 parts per million there, although it doesn't rise. And the orange is the temperature, and they look like they're in lockstep. One is influencing the other, but which one is influencing which? It's not what you probably hear most of the time. It is, in fact, the temperature that's influencing the CO2 levels. And they are somewhat hundreds of years after the temperature's gone up. That being said, the CO2 levels now are the highest they've ever been in the last 800,000 years, and you'll understand why that's a concern when I talk about the physics of these. which we'll get to. 24,000 years ago, this is the coastline of Florida. You had more land. Did you have a house here by any chance? Because it's underwater now. This is New Zealand, it's an island. Looking back here, 24,000 years or so, this is the last glacial maximum. This is when sea level was 120 meters lower than what it is today. 120 yards, if you think in those. And as the ice started to melt, that's what MWP means, meltwater pulse, the sea level rose and rose and rose over the last 20,000 years until where it is today. Unfortunately, it's still rising. Talk about that. How do we know this? Reconstruction methods are shown here, the proxy methods. Proxy measurements is what we call them. In the short term, we can use ice cores. We can actually get gases that are trapped in the ice. We can find sediments that go back further. We can look for the absence or presence of pollen, because if you know what's growing in a particular sediment, you know the growing conditions of it, so you can tell something about the temperature. But most importantly is the oxygen 16 to 18 ratio that we find in calcium carbonate. That can be related to temperature, because that ratio changes as temperature changes, so that's very important. And Dr. Fike here is holding a piece of limestone over 400 million years old, and that will have been done using the calcium carbonate, the oxygen ratio in it. Now, the comparisons that we're making today is to this base period. In 1951 to 1980, temperatures worldwide were fairly stable. So we have an average temperature over this period that is stable, and now we compare things to that. So this is anomalies, that is the difference from this average, and we find that there is an anomaly just before that base period. That's World War II, heavy industrialization, lots of stuff being put out. The place got a little bit warmer. This is the present. I mean, not exactly present, but near past to present. And as you can see, it's been warming steadily compared to the base period. Prior to the base period, things seem to be a little bit cooler. So we seem to be in a warming trend. Let's look at decades. These are the 1970s. We're looking at anomalies again. The more red the color, the higher the anomaly. So in 1970s, we actually see some blue up here. That means it's cooler compared to the base period. In the 1980s, we have a little bit of blue, but we got more yellows and oranges. Then we go to the 1990s, we still got a little bit of blue here, but more oranges and deeper oranges. Then in the 2000s, it's getting warmer again. And this is the latest data up to the end of last year. And as you can see, there's even more red in this than there was in the 2000s. So steadily, things are warming up. As it gets warmer, it gets colder. Crazy, right? There was a bad freeze in January this year, and this is what happened. That's Niagara some time ago when it actually froze due to something like this. Because we have more warmer air on the planet, it is able to intrude on the cold, stable, usually stable, polar air mass that just stays up there in the Arctic Circle. But the warmer air was able to protrude into this, disturb it. What happened? The cold air then fell over into the lower latitudes, which is why we had this deep freeze in January, at least in North America and some other parts of the world too. Because it was warmer, it got colder, if it makes sense. So let's look at some basics now about how climate is driven. So I said the only energy source coming in is from the sun. So here's the sun overhead, and it's warming the Earth there, assuming no reflection. This is the maximum energy input. It is measured in watts per square meter, 342 watts per square meter. In higher latitudes, the land is spread out a little bit more because of the geometry of it. So instead of 1 square meter, we have 1.4 square meters, and the energy is diluted over that area. So at 45 degrees, it's only 242 watts per square meter. The higher we go, the less energy impacting on the Earth's surface. This is the electromagnetic radiation spectrum, and pretty much all of this comes out of the sun, but we are really only interested in one part of that, and that is the infrared there, because infrared is what's responsible for the heating. When you put your hand up next to an electric fireplace and you feel warmth coming, that's the radiant heat, that's infrared radiation coming from the element that is hot. Now, let's not knock greenhouse gases completely, because if we didn't have any greenhouse gases whatsoever, then planet Earth would be a snowball. It is estimated that the surface temperature of our planet would be somewhere between 0 degrees Fahrenheit and minus 18 degrees centigrade if we didn't have any greenhouse gases whatsoever. So it's good to have some. We could achieve this by reducing the amount of incoming energy from the sun from 5 to 10%. How could we do that? Enough dust getting up there from something or other. If you remember mutually assured destruction in the potential nuclear war that we were looking at in the 60s, this is what would happen, the nuclear winter. So how does it work? This is the atmosphere with no greenhouse gases. The sun feeds in energy. It's reflected and absorbed here. The reflected goes straight back out to space and it's gone. And so we end up with snowball Earth in that situation. This is the greenhouse gas effect. The energy comes up from the surface of the Earth. It is absorbed by the gases, and it's not greedy. It doesn't keep it. It re-emits it again. It re-emits it in all directions, so some of it goes into space, and some of it comes back down again. And the stuff that comes down is what's concerning, because then it warms things up more. And then we have this cycle. These are some of the molecules that are greenhouse gases, and I'm sure you've heard of many of them. I'll go through them quickly. There's carbon dioxide, nitrous oxide, ozone, methane, sulfur hexafluoride, and that one there might be a surprise to you. It's water. Water vapor is actually a greenhouse gas. More about that in a second. If we look at the distribution of some of these gases in the atmosphere, you can see the bulk of it is carbon dioxide compared to methane. There's nitrous oxide, there's halocarbons, a whole group of halocarbons, and there's ozone. So this is a major player, carbon dioxide. Water is variable around the planet, so it's hard to estimate its effect. It depends where you are. But if we rank them, then this is the ranking. Water's at number 1. If we take CO2 as having a unit effectiveness in being a greenhouse gas, then everything is ratioed to that. So you see water's twice as good as being a greenhouse gas as is carbon dioxide. And as you cast your list down these names here, you'll see that methane is somewhere between 25 and 84 times as effective as carbon dioxide. Depends which study you look at. And some of them are really very effective at trapping and re-emitting heat. And when we get down into some of the more stranger molecules there. Now, they don't stay in the atmosphere forever. Obviously, water's there, it's not applicable. If I inject a bolus of carbon dioxide into the atmosphere now, it will stay there somewhere between 30 and 95 years. I think that's 95, yes. Methane, which you've heard is so bad, will only stick around in the atmosphere about 12 years, because then it's changed into something else. It's used up in the carbon cycle, or it's oxidized to carbon dioxide and water. And so all of these things have lifetimes. They don't stay there forever. But we keep re-emitting them, so we keep increasing their concentrations. So an extra 4 watts per square meter will increase the temperature of the Earth by 3 degrees. That's the climate sensitivity that's been estimated. It could be a slightly different number, and we're not sure, so this is our uncertainty here. So if we go here from 400 parts per million CO2 in the atmosphere up to 800, we will get a 3-degree rise if this constant is correct. How sure are we that that constant is correct? How sure are we the climate sensitivity is correct? We've measured it and we've modeled it. So it can be measured and it can be modeled, and these are the results of all the studies. Cut to the chase here, this is the average of all of those studies over on the left, and the average value of those studies is 3. It can range from 1.8 up to 4.6. We're in serious trouble if it's 4.6. It's not so bad if it's 1.8. We're using 3. 3 seems to work. It seems to match the predictions. This is our energy budget. So there's the 340 coming in. It's absorbed here. Some of it goes down into the deep earth. Some of it's being reflected here off clouds. And over on the other side here, we have the energy in the greenhouse system. We've got energy coming back up. It's absorbed up here by gases. It's coming back down. So we've got this cycle here. These are the numbers that we are concerned with. And then there is some that's being lost into space. We do not want to be increasing this value here, because this value will increase and things will continue to get warmer. How does that happen? Well, we'll get to that in a minute. This is from the NCA4 2018 report. It's a US report, and what you see on the screen here are indicators. They are all indicators that indicate that things are warming up. And the direction they're going all agrees with the fact that things are warming up. So it would be nice, you know, if some of those indicators said, no, things are not warming up. But they don't. They all agree that things are warming up. And this is the actual page I took that from, and these are all the indicators and how they're going in the wrong direction, if you like. They're indicating that things warm up. Now, some people think the sun is responsible for what's going on. So let's talk about the sun briefly. This is the solar irradiance in watts per square meter. It's a very expanded scale, and you can see it goes up and down slightly, and it's been going down there. This is the carbon dioxide level. There's the scale for carbon dioxide. Talk more about that up and down in a second. And these are 3 studies here looking at the temperature on planet Earth. And you'll notice that this line and this line don't agree with that one. So that's not a reason. What about sunspots? Because sunspots can also affect what's coming out of the sun. This is the average number of sunspots, and this is the actual number. So this is a moving average. And as you can see, it's going down here. And we have the carbon dioxide going up, and this is a different display of temperature. It's going up. So these don't agree either. So sunspots are not it. Indeed, we haven't seen any increase in solar output as measured by the satellites from the sun over the last 50 years. We find that nighttime temperatures are going up faster than daytime temperatures. Well, that makes no sense because the sun doesn't shine at night. And we also have stratospheric cooling, which again, closer to the sun, you'd think, well, if there's more energy from the sun, it would warm up higher in the stratosphere than down on the surface. No, nothing is consistent with solar effects, but it's all consistent with greenhouse gas effects. Now, what about the sea? What's going on in the sea? Where's the heat going? So this little line here, these lines here, are air, land, and ice, and this is where extra heat is being stored. The bulk of it is going into the oceans. You see in the deep ocean and in the upper ocean. This is measured in something known as zeta joules. It's a unit of energy. What's zeta? Zeta is 10 to the 21. That's a 1 with 21 zeros after it. So these are really big numbers. There's a lot of energy being stored in the sea. And that energy can come back out in the form of hurricanes. And you've noticed they're getting stronger too. This impacts the sea level rise. 42% of the rise in the sea so far is due to the heating. These are tidal gauge measurements since 1860, steadily going up. This is satellite measurements, so this number and this number should be about the same, but they're presented in different scales. This too is continuing to go up, and that's the rate of change. So that's the latest measurement, which I just looked up before I came here. It's gone up 9 centimeters and will continue to rise. Now, that's an average number, because if we look at different parts of the Earth, then you see these arrows here, they're different lengths. That's feet per century, how much is going up, and you'll notice that some of them are going down. So it's not going up everywhere, somewhere it's going down. Why is that? That's because in those areas the land is rising. It's still an elastic rebound from when the glaciers were sitting on them 22,000 years ago. So that's still occurring, particularly in the Baltic area and around England, also around here too. The land is coming back up as the weight of the glaciers went away. Northwest Passage originally opened in 2007 when a ship actually could go through it, expected to be ice-free by the end of the century, and you can see in the satellite images over here, September 2015, the Northwest Passage is open. September 1979, the Northwest Passage was not open. And in fact, a cruise ship has already gone through it. This was the first one in 2016. The Crystal Serenity went through it, and it did it the following year after. I'd love to have been on that ship, see that there. The carbon cycle is something we all need to know about for this, and this is complicated. The red here is what we're doing, and these numbers are gigatons of net carbon. So that's the weight of net carbon being put into the atmosphere. If you were to convert these numbers to carbon dioxide, those values would be higher. So there we go, 9 gigatons going up into the atmosphere. nature's helping. It's taking out 3 of them in photosynthesis, so it's helping get rid of some of this excess. The ocean's taking up 2, so that's going into the ocean there, and hopefully, you know, that gets locked up into the natural system in the carbon cycle, but that unfortunately still leaves 4 gigatons per year going into the atmosphere, which is 4 billion tons, if you don't know what giga is. These are the CO2 measurements from Mauna Loa. So as you can see, from 1960, steadily rising up to today. These are the latest data from Mauna Loa, showing you the parts per million concentration from last year to this year in March. And we've been above 400 parts per million since September 2016. So we crossed a threshold at that point that climatologists were a little bit worried about. Now, this zigzag pattern is due to the nature of plant growth and plant death in the northern hemisphere as it takes up more CO2, and then during the winter that photosynthesis process is diminished. Modeling. We get a lot of information from modeling. So this is a climate model, and as you can see, it's complicated. And up until recently, until we got supercomputers, we could not deal with something this complicated. We could only deal with a portion at a time. How are we doing with modeling? Well, we come up with a model, we make a prediction, we look at observations, and we see how the prediction meets the observations. It's crap, we go back, we refine the model, we do it again. We go round and round and round till we get it right. And do we get it right? Well, you could be the judge of that. This is 14 models with different sets of input parameters, because you can change the way you run the model. So each one of these yellow lines is a different output from the 14 models. So we've got 58 up there. The red line is the model average. The black line is the observed temperature anomaly. Are we doing well? You can be the judge of that. Now, there's one thing that we can do that's really interesting. So this is the picture you just saw, and we can take all the human parameters in the model and turn them off, and we can see what the natural climate should be doing, and this is what it should be doing. In other words, we're seeing an observed temperature rise, and without human conditions, we should actually be in a cooling trend. We should not be warming up, and this is what all climatologists know. We should be in a cooling trend. When we make a prediction, we're never really sure whether that prediction is going to be okay, but as time passes, and this was published in the New York Times just last year, we can look back. So 1988, Hansen and his group made predictions about what was going to happen to the world's temperatures. They created 3 scenarios, A, B, and C. The black line now is observations that we can go back and compare his predictions from 1988 to what actually happened. How did he do? Not bad with scenario C. We have good confidence in our models. This is the ice-free limit in the northern hemisphere. This is if we do nothing, i.e. we don't change any practices. We are going to be ice-free certainly by about 2060. This is if we are able to reduce greenhouse gases drastically, which is not going to happen, actually, because we're just not that good at doing this. So it's going to be somewhere in between. We may be able to save ice in the northern hemisphere. We may not be able to, based on these predictions. Sea level, these are the proxy records going back to 1800. This is tide gauge data. This is satellite data. You can extrapolate that line. It's going to be somewhere in here. Sea level by the end of the century is going to rise somewhere between 1 and 4 feet, or 0.3 and 1.2 meters. And it will continue to go up at that point. This is temperature projections by the end of the century. These are the optimistic policies. We're hoping that we can keep temperatures as low as 3 degrees. This one down here is if we are really, really good at cutting greenhouse gas emissions, we'll keep it at about 1.5 degrees. But if we do nothing, again, it's going to get warm, up to about 5 degrees. Or even higher. What influence are we having on the planet? What are we doing? Well, one of the things we're doing is this. We keep cutting these down. These are a carbon sink. They're using carbon to grow. The photosynthesis is taking CO2 out of the atmosphere. They do breathe, so they are putting CO2 back in the atmosphere. That part kind of cancels out, but the fact that we're cutting down is we're removing that carbon sink as we clear more and more trees. Cement, we keep building things. Gosh, we keep building things. And for every ton of cement that we build, the whole production cycle in making that and building it, using it, what have you, is emitting another ton of CO2. So ton for ton, we're getting that. It doesn't sound like it's too bad, but if you look at the amount of cement produced in 2017, 4.1 gigatons of CO2 came out of that, because that's how much cement was used. And it's expected to rise by 2030, going up to near 5 gigatons. So we keep building and we keep emitting CO2. This is a summary of what I showed you on the more complex picture. This is what we're putting into the atmosphere. This is what nature's taking out into photosynthesis. This is what the ocean's taking out, leaving this balance that is in the atmosphere. And why is that important? We'll get to that in a second. Looking back into the past, we find something very interesting, actually. Here we go back to 8,000 years. Expanded scale, carbon dioxide. And we see about 8,000 years ago, what we observe is the CO2 levels were rising as compared to what was expected. And this is the Industrial Revolution, of course. What does this coincide with? This coincides with the advent of agriculture. So we've been messing around with the atmosphere for about 8,000 years. And then as we started more and more animal husbandry, this happened about 5,000 years ago, the methane started to go up. And we all know that cattle are a great source of methane. So yes, we've been doing this for a while. Now, we can get into some unfortunate feedbacks. So here's an example. I'll give you two examples of feedback loops that we don't want to get into. So global temperatures get a little bit warmer. That's a perturbation. What happens? The oceans get a little bit warmer. The solubility of CO2 in the water decreases. More CO2 comes out. And because it's a greenhouse gas, it can absorb and re-emit more radiation, and the planet will get warmer. So we get more outgassing from the oceans, we have a stronger greenhouse effect, and we get warmer global temperatures. This goes round. This is an amplifying feedback loop. As the oceans get warmer, more stuff comes out, it gets warmer. We don't want to get into an amplifying feedback loop. Similarly, this one actually really scares me. This is the permafrost feedback. So increased CO2, we have increased temperatures, particularly at higher latitudes, which we're seeing now. We have thawing permafrost, which we're seeing now, and that will release methane and CO2 from the permafrost because it's trapped in the permafrost. Why is this scary? It's scary because of this one, this statistic. There's about twice as much carbon as currently in the atmosphere locked up in the permafrost. So if you were to melt the permafrost immediately, which is impossible, but if you were, you would triple these concentrations overnight, and we will be in serious trouble. This is permafrost area, up in the north, of course. There's a lot in my country, and there's a lot in this area. We're sort of going over this area here. Now, as that melts, the land begins to buckle. Things built on it will tend to sink, and we see evidence of this now. These are kettle lakes. This is sandy soil. The only reason there is water held in the kettle lake is because of the permafrost locking it from underneath. This is what's happening now. The kettle lakes are disappearing because the permafrost in these areas is going away. I have to do this because we're on this ship. Tourism. The fact we're on this ship, we're contributing to the problem, unfortunately. These are all airline flights. These are the total emissions estimated for 2013, 4.5 gigatons. Unfortunately, it's predicted to go up by 2025, 6.5 gigatons. So, and as you see, published in Nature Climate Change, an estimate of 8% contribution to the total greenhouse gas emissions comes from us having a good time. The irony of that. This is something nobody talks about. I talk about it because it's scary. This is population growth since 0 year, i.e. 2,000 years ago. I was born here in 1950. Since I was born, the Earth's population has tripled. It's gone from about 2.5 billion to 7.5 billion. That's scary. We expect it to peak at 11.2 billion in the end of the century for a very conservative, optimistic reduction in greenhouse gases by the IPCC, International Panel on Climate Change. They're thinking it's going to peak at about 9 billion. I don't think that's going to happen. Why is this scary? Well, there's more of us. We want to clear more land. We want to build more concrete structures. We want to use more resources. We want to drive cars. We want to fill them up with petrol. And we all want to have a good lifestyle. And unfortunately, some of these things emit greenhouse gases. More of us, more greenhouse gases. This is the per capita emission of carbon dioxide in metric tons. And so there's the scale there, going from 0 to 20 metric tons. Saudi Arabia leading it. Well, they don't have too much of a population there. Don't forget, this is per head. Canada and USA right up there. Population of USA about 10 times that of Canada. This looks good down here. India's lowest on the scale, but don't forget there's 1.3 billion people there. Multiply that by 1.3 billion for their total emissions. It's a lot. 27% of CO2 emissions are coming from industry. Is there any way we can clean up our industry to reduce that? Well, that remains to be seen, of course. Now, some outcomes from climate change. That goes through some very quickly. Farming, pests come earlier, they stay longer. There's increased crop losses, and that, for you and I, means prices go up. Are we looking forward to that? No. This is an unfortunate one. This is the king penguin colony. They have, over the last 30 years, declined in numbers by a factor of 10, and it is estimated that by the end of the century, about 70% of them will have gone, either died off or will have relocated due to the climate change in that area. They're located there. The Hawaiian island chain. This is the Hawaiian island chain. There's the big island. There's the islands you're probably familiar with. We're talking about this one here. It's gone. It's been washed away. It's not the only Pacific island that has now gone due to a combination of rising sea levels and increased storms. And in fact, there's been a couple of islands where populations have had to move. That will continue. This is the first casualty. The humble bramble K. melamis. It's lost its environment due to storms and reduction of land. And it is now the first casualty of at least a small rodent in climate change. So they're gone. So myths and fallacies I want to go through fairly quickly. You may have heard some of these. There's lots more. I could spend a lot of time talking about this, but I don't have the time. So you may have heard this one. So the fact is, in fact, that we are responsible for almost all of the increased CO2 in the atmosphere today, which we are measuring on a continual basis. This is countered sometimes by people telling you that volcanoes produce more carbon dioxide than what we do. That's a myth. The fact is that while volcanoes do indeed produce CO2, the amount of carbon dioxide that comes out of the volcanoes is a small percentage. It's about 7% of what we are putting into the atmosphere. That's actually 7% of the excess we're putting into the atmosphere, because we're putting more than 4 gigatons in. We're putting about 9. You may have heard that Antarctica is gaining sea ice. You may have heard that. You may have also heard that it is losing land ice. And it is the land ice, of course, that we are concerned with. That's the fact. Both those things are happening. It is gaining sea ice and it is losing land ice. The myth that counters this is simply that Antarctica is gaining ice. Well, yes, true. Sea ice, not land ice. So this is a myth, a fallacy of emission. In fact, what's going on, you can see here, this is March and September in Antarctica, the way the sea ice increases in the winter down there and the way it decreases in the summer. So error of emission, you've got to remember the difference between them. This is the ice loss in Antarctica from about 2004. This is the ice loss in Greenland since the same date. This is the rate of change in gigatons per year, so that's billions of tons per year. Again, this is the rate of change. also in gigatons per year. The Antarctic ice sheet is disappearing 3 times faster than it did a decade ago. The worrying thing about this decrease that we have in both the ice sheets is the ice sheets are melting at an accelerating rate, and we can't model that, so we don't really know how long they're going to last. What's the future? Well, the future's not as bleak as I'm painting it. Some countries are doing very well in renewable energy. There's us, Canada. There's the USA, some improvement there. And so the darker the color, the more renewable energy that that country is using. And hopefully, as time goes by, all of those countries will go darker in shade. Wind power is coming along. This graph here shows you the increase in wind power and also in solar power. You've probably seen these everywhere. The Gansu wind farm is coming online in a few years in China. That's going to have enough energy for about 4.5 million homes, so that's a big station. The USA would need about 600,000 turbines. That would take up an area of Rhode Island if you could find an area where the wind blows constantly. Because obviously if the wind doesn't blow, the turbine doesn't turn and there's no electricity. And Denmark creates about 44% of its power. Now, the argument against wind turbine is often that it will destroy ecology, lots of birds get killed, and they're just terrible. We shouldn't be using them. So down here, this is windows. This is the amount of birds that die in windows. And this is wind turbines here. And this is cars. They fly into windscreens. And then there's some other causes there. Where's cats? That's cats. Right, okay. This too shows the same sort of thing. This is comparing wind energy, nuclear power, and fossil fuels. And if we were able to eliminate fossil fuels, we would save 70 million birds a year if we could eliminate them. But we can't eliminate that yet. We can try and fix CO2. Who's been to Iceland? Yes, did you go to the geothermal plant there? Yes, so you saw what they're doing there. They're actually taking CO2 out of the air. They're injecting it into the ground. And much to everybody's surprise, this mineralized much faster than they anticipated. They can get rid of about 40,000 tons per year this way. And in fact, anywhere that has the right geothermal properties can do the same thing. They can pull it out. But unfortunately, we need to fix 4 billion tons per year to be able to make a difference. Then there's this one that has just been published where we can take CO2 right out of the atmosphere and make it directly into all of these materials here without having to use any fossil fuels to do that. There's nuclear, of course. If we want to get to this point here, which is basically 0 emissions of CO2, what energy source are we going to use? Well, the UN report says that we need more nuclear power. This is one coming online in China fairly soon. Actually, it's already online. We are only producing about 10% of our power right now worldwide with nuclear. When I was in Mexico a few years ago, they gave the green light for 3 nuclear stations to be built there. The justification was basically, glibly, when the wind doesn't blow, the turbines don't turn. And when the sun doesn't shine, the photoelectric cells don't photoelectric. So what are we going to do for core power? They're going to go nuclear. What's the way forward? Well, several ways. Obviously, try and reduce fossil fuel use. It would be nice if we could do something about population growth because, of course, that's a big factor. As I said, nobody wants to talk about it. We've got lifestyle changes, cement construction, that would be good, reduce deforestation. And one of the things that perhaps we can do if we insist on building things out of out of concrete, is to find something that doesn't emit as much CO2 during that process. Try and find a better method of making it. This is what's currently happening based on the country's policies. Unfortunately, this is my country, and the way we're going right now, if we continue to do that, then the increased temperature on planet Earth is going to be about 4 degrees centigrade, which is not good. If it's orange here, you see there, for example, it's less than 3. If it's gray, which is there, or black, it's going to be 4 degrees and more. So these countries need to do more. The only one that seems to be doing the right thing is here on the coast of Africa. It's less than about 1.5 degrees. So we need to emulate what they're doing. Why is this important? This is important because of these tipping points. What's a tipping point? A tipping point is something that we can control up to the tipping point, and once that tipping point is exceeded, we can't control it. One of the tipping points that we're getting very, very close to is the Greenland ice sheet. If we raise the temperature very much more on planet Earth, the Greenland ice sheet will destabilize and it will melt. What does that mean? That means an increase of a few meters in sea level fairly quickly, as opposed to the Antarctic ice sheets, which will do worse. You see, the West Antarctic ice sheet is in trouble. It's anywhere between 1 and 3 degrees rise. The East Antarctic sheet, we've got a little bit of time based on the colors. So those are all tipping points that could be important. Renewable energy is supplying lots of jobs, and this is job growth. It's increased 5.3% over the last year. This is for worldwide figures, and that's how many jobs were created in 2017. That was over 10 million jobs in renewable energy. So it is an area of active work and research, of course. Can we take CO2 out of the atmosphere? That's what negative CO2 means. Can we remove it? Well, yes, we can. This is a cost breakdown of how you might do it. The cheapest way to do it is, in fact, plant more trees instead of cut them down. And then all the other things that you see there, they become more costly as we go along. This is a pilot project. There are actually 2 that have been built by Climeworks. One's in Switzerland, one's in Italy. More to come, apparently. They can take out not too much, only 50 to 150 tons of CO2 per year. So if we want to remove 1% of the CO2, you're going to need to build 250,000 plants somewhere. Then there's another company that's working on this. This is still in principle. This is Carbon Engineering. They claim they can remove 1 million tons per year, so you won't need too many of these plants. Well, not 250,000. They also say that they can take the CO2 that they've removed from the atmosphere and turn it into a synthetic fuel. That seems to be counterproductive, because when you burn fuel, you get CO2 again. Yeah, I don't understand that. And that brings me to the end of climate change.